Hello and welcome to another video of Wise Interactive Learning. In this video, we are going to follow up unnecessarily logarithmic differentiation, the composite function differentiation and inverse trigonometric differentiations. So after these three, we can say we are enough equipped to well know what are the differentiations of implicit differentiation and parametric. So before we start, we'll like to define them. What are implicit? So implicit necessarily means that it is nothing but it is in a complicated manner to sort out, right? So the given expression, so any kind of expression given to you will necessarily be in a complicated form. For example, let's take y equals to x square plus 5x plus 3, right? And at the same time, if we take y square equals to 3y plus 2x square plus x, and if you are to ask what is dy upon dx and which one will be easy, so it is straightforward that the first equation over here, which is y equals to x square plus 5x plus 3, this will be far more easier, right? Easy. But in fact, if you resolve or try to jump onto all the equations, you can say that even this is also some kind of easy example, but we need to rearrange all the terms. Rearrange terms, right? And when are we going to rearrange them? We are going to rearrange them in such a way that at the end of the our solution, we have dy upon dx on the left hand side and the remaining the answer we have on the right hand side. And in specifically implicit function differentiation or rather any kind of differentiation, it doesn't matter if the right hand side consists of any y's, like the terms y in itself. So it can be y, it can be 2y, or it can be anything as opposed to the previous examples which we have seen for logarithmic and other functions. But what is parametric? So I'll just take a fresh page over here. So what is parametric? So parameters are nothing but some things which are changing over specific values. For example, if you take the value of sine, so if you take sine graph, so you can say that what is the parameter over here? So as the sine theta changes, so if this theta changes, the value over here it will go from -1 to +1. So at this top value it will be 1 and at the lowest value it will be -1. This is for sine theta, right? So what is the parameter over here? It is the theta. So what is parametric differentiation? It is nothing but, so let's say that if you have on x equals to sine of theta and if you have y equals to cos of theta. So in this case you cannot directly find, so you cannot directly find dy upon dx, right? And this is our required equation, like this is what we always want, which is the differentiation. So in this case, what are we going to use? So what we can do is, see, x is essentially a function of theta, like which is the parameter. So what we can say is dx upon d theta, right? And it will be cos of theta, since the differentiation of sine is cos. And also we can say that dy upon d theta is nothing but minus of sine theta, isn't it? And now we can say that from this dy upon dx can also be written as dy upon d theta completely divided by dx upon d theta, and if you simplify that you will get the same answer. And now we have two things over here, right, which is dy upon d theta, which is over here, and dx upon d theta, which is over here. And you can simply replace this all terms and the answer will be minus of sine theta upon cos of theta, right, which is going to be minus of tan theta. So what we have got is dy upon dx at the end of this term, and this is nothing but parametric equations. Obviously the examples are not going to be such easy on easier level, but in nutshell this is the concept of implicit and parametric. So now we'll move on to questions. So we'll take the first question. So first question states that y cube minus 3y square x equals to x square plus 3x square y. So now this is from the problem of implicit function. So this is given in a complicated manner. What we can do is either we can resolve it in such a way that it is linear, like in straight, and we can directly take the all the differentiations, or we can take x terms at one side, y terms at one side, and then we can differentiate. In this case it is very straightforward, so we can do this. So when you differentiate y cube, it will give you 3y square times dy upon dx, isn't it, minus 3 times, now we have to differentiate y square x. So y square, if we keep constant, x differentiation is 1, plus x 2y times dy upon dx. Now on the right hand side we have x square, which is over here, so differentiation is 2x plus 3 times, so you have x square y, so x square if you keep constant you get dy upon dx, plus now you have to differentiate x square, so you have y times 2x, and now you can see that we have 3 dy upon dx over here. So this is the first one, this is the second one, and this is third term, but still you have to multiply it with 3 over here and 3 over here. So we will take all the dy upon dx terms on the left side. So on the left side we have 3y square times dy upon dx. I'll just rearrange this. So on the left hand side we have 3y square dy upon dx minus 3 times this entire term, which is 3 times x times 2y dy upon dx. Obviously this is going to be 6xy. Then this is having a plus sign over here. When it comes on to the left side, we have it as negative, which is going to be minus 3x square dy upon dx. Now here we have taken the first term and the third term, so second term is going to be on shifted on that side, so 2x plus 3y squared, right? And then here we have plus 3y times 2x. So we need to simplify all these terms, so we can say that this is 6xy, then we have 3y squared over here, so which is negative, and then we have 3x squared, and here we have this as 6xy, so you have 2x plus 3y squared plus 6xy on the right side. And since we have taken all these terms out, what we have remaining is dy upon dx. So your required answer is this, which is dy upon dx. So what is your answer going to be? So when you divide this whole term over here, you will get your final answer. But before that, we can do a trick over here. We can take out 3 common from all the terms. So here you have 2x plus 3y square plus 6xy, everything divided by 3 times y square minus xy minus x square. So this is your final answer, which is very easy and convenient. So in case of parametric, I am not going to define all the steps, rather I am going to tell you a short trick in which you can do your calculations in your head, and this is going to solve a lot of problems for you in future also. So first we'll take an example, which is x equals to sine of log t, and you need not worry because these are not very complicated examples, but it is going to be easy for you to understand why I am doing this. So I'll take few examples which are easy to solve, easy to crack, and it will make sure that you get the idea from the core. And second example is e raised to cos of 2t and y equals to e raised to sine of 2t. Fine. So in this case, what we are going to essentially see that x is a function of t and also y is a function of t. So here the parameter is nothing but t, and in this second question also the parameter is going to be t. It can be anything, it can be theta, it can be alpha, any kind of parameter. Just make sure that in each and every example of parametric equation, the parameter which is going or changing should always be equal. You cannot differentiate two different functions x and y when the parameters are different. For example, if in the y equation, if here the t function was replaced with sine of theta, then you essentially can't do differentiation, right? So it's very basic and easy to understand. So I'll start with the fast process of doing this. So you know that you have dy upon dt and dx upon dt as your final answer, right? So we'll directly get dy upon dt, which is going to be the product rule, it is going to be the chain rule. So in case of chain rule, you know that first you have to differentiate log and then you have to differentiate sine. But as I know that eventually I have to multiply it, I'll directly first differentiate what is sine t, which is cos of t, and log of sine t, it is going to be sine t, everything divided by, so differentiation of dx upon dt, it is going to be cos of log of t times 1 upon t, because the differentiation of log of t is 1 upon t. So here we have cos of t upon sine of t, it is going to be cot t times t. So you have this t over here going into the numerator, and in the denominator you have cos of log of t. So this is your final answer. So I'll just drag it over if you can't see. So dy upon dt, you have cos t upon sine t and cos of log of t divided by t. So this t will essentially go into the numerator, and since here it is cot t, it is going to be t times cot t cos of log of t. So this is your final answer. Now we'll see the second question. So in the second question, this is basically the easiest example. So dy upon dt, everything divided by dx upon dt is going to be a final answer. So we'll in one to two steps we'll try to differentiate it. We know that for any function e raised to f of x, when you try to differentiate this, your answer is going to be e to the f of x times f dash of x. So your original terms are going to come as it is. So let's write those. So dy upon dt is going to be e raised to sine 2t. Now you have to differentiate sine of 2t, which is going to be cos of 2t, times you have to differentiate 2t, which is going to be 2, since you are differentiating with respect to t. Now e raised to cos of 2t, then again you have to differentiate cos of 2t, which is going to be minus of sine 2t, times you have to differentiate 2t, which is going to be t. So 2 gets cancelled, and this is your final answer. But here we can still simplify this. It is going to be e raised to sine of 2t, everything divided by e raised to cos of 2t. Now only the issue here we have is a negative sign, so that negative sign will go over here, and we have cos of 2t upon sine of 2t, which is going to be cot of 2t. So that's your final answer. So in this way you can solve each and every example regarding to your board examinations or JEE examinations with respect to your parametric differentiation.